Students, in this class, we are going to study the equilibrium and its conditions. So basically, conditions of equilibrium are mainly the equilibrium. When you say equilibrium, you are referring to the conditions. There are two conditions for an object to be equilibrium. Conditions for equilibrium. There are two conditions for an object to be in equilibrium. The first condition is there should not be any net force on the object. So there are two possibilities. Either there must be no force at all, or the forces, if they are present, or the forces must be balanced. So in any case, there will not be any net force. So the first condition of equilibrium is about forces, and it says that there should not be any net force on the object. The two possibilities are either there will not be any force at all, or the forces will be balanced. The second condition for equilibrium is it is about moments, and the other name for this condition is, we call it principle of moments. Principle of moments. And this condition states that for an object to be in equilibrium, the sum of clockwise moments. Now, moments are calculated about a point. So while applying principle of moments, since the object will be in equilibrium, so you can take pivot anywhere. So when the object is not rotating, the pivot can be taken anywhere. So it should apply to all the points. So for an object to be in equilibrium, the sum of clockwise moments about a point will be equal to the sum of anti-clockwise moments about the point. This condition is called principle of moments. According to this condition, the clockwise and anti-clockwise moments must be balanced. So whenever we check equilibrium of an object, we apply these two equations. Now let's go with some examples. Let's suppose we have a situation in which here it's a wall, against this wall we are balancing a rod. The rod is right here. And this example, the rod is horizontal. And assuming that the rod is uniform, the rod is supported by a rope. So this is the rope. Now the length of the rod is, just for example, L. First of all, the rod is uniform. First of all, the rod is uniform, which means that the weight will act in the center. The weight of the rod will be acting in the center. The rod is uniform. Its length is L. Its length is L, and it is in equilibrium. So the rod is uniform, its length is L, and it is in equilibrium. And this angle is given, and this angle is called theta. This angle is called theta. And the rod is, just for example, hinged here, and this point will become the pivot of rotation if the rod rotates. If the rod rotates, this point will become the pivot of the rotation. So this is a uniform rod, its length is L, and the rod is in equilibrium. The first part of the question is list the forces on the rod. So the first question is list the forces on the rod. The second question, so list the forces on the rod. The second question will be apply second condition. Apply second condition. This is B part. This is B part. Apply second condition of equilibrium to relate apply second conditions of equilibrium to relate mg and tension in the rope T. So mg and tension, if you want to relate them, then apply second condition of the equilibrium. And the C part of this question is, for example, C part of this question is why is it compulsory? Why is it compulsory to have a third force or a force? So why is it compulsory to have a force or a third force other than T and, so why is it compulsory to have a force other than T and mg for the rod? So why is it compulsory to have a force other than T and mg for the rod to be so T and mg for the rod to be in equilibrium? So basically the question is that if the rod is to be in equilibrium, then there should be some other force other than T and mg. This is the question. So the question has three parts in total. The first part is list all the forces. The second part, try to list the forces basically. The second part is about apply second condition of equilibrium to relate mg and T. Here the pivot is not mentioned. When the pivot is not mentioned, then you can take it anywhere. When the pivot is not mentioned, it can be taken anywhere. When the pivot is not mentioned, then you can take it anywhere. And the third part is after applying the second condition of equilibrium, yet why is it need for the third force to bring equilibrium? So these are the three parts. We will proceed one by one. The first part of the question is about listing the forces. So if we list the forces, this was the wall, and then this was the rod, this is wall, this is rod. So why is it compulsory to have a force other than, now list the forces. The A part is about listing the forces. So there are three possible forces in total. One of them is the weight, the other force is tension, and the third force will be at the point of contact between the rod and the wall. For example, the first force is the weight of the rod. The second force is the tension in the rope. The third force will be at the point of contact of the rod. For example, this point of contact is called point P. So at point Q, it is the rope that is pulling. At point M, it is the weight that is acting. And at the third point, that is point P. So at point P, there will be a third force that will be acting. So the answer to this part of the question will be, the question is, list the forces. The forces are tension, weight, and so forces so the forces are T and mg, and the third force will be acting at the point of contact between the wall and the rod. So we'll say that forces are T mg so forces are T and mg, and so forces are T and mg, and a third force may be acting Forces are T, mg, and a third force acting so forces are T, mg, and a third force acting at the so the forces are T, mg, and a third force acting at the point P. So these are the three forces in total. Now these are the forces. The B part of the question is applying second condition of equilibrium to relate T and mg. For example, if we take the point of contact as the pivot, why? Because if you take point of contact as the pivot, then the contact force will be eliminated. So to solve one equation, we need one variable. To solve one variable, we need one equation. To solve two variables, we need two equations. To solve three variables, we need three equations. Here, there are three forces: tension, weight, and third forces. So this is the wall. With this wall, we are supporting a rod. For example, if this is the rod, then the forces which are prominent and they are given, one of them is the tension in the rope. So on this rod, the three forces will be T, mg, and the third force could be at this point P. So this point P will determine we can take it to be pivot. Now they're asking about write the equation of equilibrium, or say second condition of equilibrium to relate T and mg. So we will take P as pivot. So here one of the forces is T and the other force is mg. You see mg is already perpendicular. The two forces are T and mg. And if we apply second condition of equilibrium, let me share the screen again. The share is stopped. If we apply the second condition of equilibrium for this situation, then we can write that clockwise moment will be equal to the anti-clockwise moment. So the principle of moments is sum of clockwise moments is equal to sum of anti-clockwise moments about a given point. So clockwise moment must be equal to anti-clockwise moment. So an object in equilibrium will not have any rotational acceleration. Now mathematically, it can go like clockwise moment would be due to mg. So mg times so it would be mg times the distance is an anti-clockwise moment will be if we resolve t, the two components will become so the equation will be t times so mg times L by 2, that is the clockwise moment, will be balanced with the anti-clockwise moment. That would be, first of all, we have resolved t. The components of t will become t sine theta, and this one will become t cos theta. We are going to ignore t cos theta. We will only take t sine theta, which is perpendicular. So it would become so mg into L by 2 will be equal to t sine of theta into L. So this is the equation. This is the equation, and if we simplify it further, it would become so mg into L by 2 is equal to t sine theta into L. This is clockwise moment is equal to anti-clockwise moment. So the final equation will become mg times L over time is equal to L times t. So t sine theta will be multiplied with L. So this is clockwise moment is equal to anti-clockwise moment. Now the next question is why we need a third force, C part. You see, T and mg are totally in different directions. If they are the only forces, then they can never be in equilibrium or balanced, because the two forces in different directions can never be balanced. If you look carefully, T is here and mg is vertical. So a third force must be there that will bring a balance or equilibrium between this T and mg. So even if this is T and mg, so weight is always vertically downwards and tension could be anywhere according to calculation or the requirement of the question. So in the C part, we will say that T and mg, T and mg are in different directions, hence cannot be balanced. We need a third force to balance them. we need another force. We need another force for equilibrium. So we need another force for equilibrium. Because the already existing forces cannot give an answer of 0 Newton, they could be in different directions. So forces which are in different directions have been added to give a 0 force. So T and mg are two forces which are in different directions and can never cancel out each other. That's why a third force is needed, and this third force so that a third force must be added, and this third force will pass through the point of contact. So this was the class for equilibrium mainly.